Hello there, and welcome to The Sleepy Astronaut, where the universe's most extraordinary moments unfold in gentle detail and stellar mysteries take their time to reveal themselves. Tonight's mesmerizing journey explores one of the most spectacular displays of cosmic power witnessed in recent memory. A solar eruption so magnificent it carved a canyon of fire stretching 250,000 miles across our nearest star. But before we dive into this breathtaking celestial drama, I'd love to know where in the world you're watching from and what time it is for you right now. Fitting, isn't it? A video about a solar eruption, and here we are scattered across time zones, each of us witnessing this cosmic story unfold in our own unique moment under the same sun that created this incredible spectacle. If you find this cosmic voyage fascinating, or simply a perfect way to unwind after contemplating the vastness of space, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little corner of astronomical wonder reach others who might crave a peaceful pause filled with stellar majesty. Now, I do hope this isn't so captivating that it keeps you awake, but if it does, well, at least you'll have learned something remarkable about the dynamic nature of our solar system before you drift off into dreams of distant stars' dreams. So settle in, let your thoughts wander toward the heavens, and let's begin. Because somewhere between plasma and magnetic fields, between eruptions and cosmic forces, lies the story of July 15th, 2025. On that extraordinary summer day, our sun, the seemingly steady beacon that rises and sets with comforting predictability, decided to remind us just how dynamic and powerful it truly is. What unfolded was nothing short of astronomical theatre, a performance of such scale and intensity that it left astronomers around the world both mesmerized and humbled by the sheer magnitude of stellar forces at play. Imagine, if you will, looking up at our familiar yellow star and witnessing it suddenly tear open, revealing a glowing canyon that stretches further than the distance between Earth and our moon. This wasn't science fiction or an artist's dramatic interpretation. This was reality, captured in exquisite detail by our most sophisticated solar observation technology. The event began with what solar physicists call a filament, a structure that sounds deceptively simple but represents one of the most complex and fascinating phenomena in our solar system. These aren't mere surface features, but massive arches of plasma held suspended above the sun's surface by invisible magnetic forces stretching hundreds of thousands of kilometers into space, like bridges made of fire and light. On July 15th, one of these colossal structures became unstable, and in a display of cosmic violence that defies earthly comparison, it erupted. To understand the true magnificence of what occurred, we need to appreciate the scales involved when we talk about solar phenomena. We're not discussing anything remotely comparable to terrestrial events. The canyon of fire carved by this eruption spans roughly 250,000 miles, to put that in perspective. This fiery chasm could comfortably contain the entire distance from Earth to the Moon, with room to spare. Imagine a trench so vast that our entire planet would appear as a tiny speck within its depths. This is the reality of solar dynamics, where even minor events dwarf anything we experience on Earth. But the canyon's length tells only part of this remarkable story. The walls of this stellar chasm tower at least 12,400 miles high, making them nearly 2,000 times deeper than Earth's deepest ocean trench, the Mariana Trench. These aren't gentle slopes either, but towering cliffs of superheated plasma, glowing with the intensity of stellar fire. Each wall of this canyon represents temperatures that would instantly vaporize any known material, creating a landscape that exists only in the most extreme environments of the universe. The plasma involved in this eruption wasn't ordinary matter by any earthly standard. We're talking about material heated to temperatures of millions of degrees, where electrons are stripped from atoms, and matter exists in a state so energetic that it becomes luminous, flowing like liquid light through magnetic channels in space. This plasma dances to the rhythm of magnetic forces, invisible to the naked eye, but powerful enough to suspend billions of tons of material against the sun's tremendous gravitational pull. What makes this event even more extraordinary is that astronomers were watching before it happened. For days leading up to July 15th, solar observers had been tracking an unusually large filament, a dark ribbon of cooler, denser plasma suspended above the sun's surface like a cosmic tightrope walker. These structures are fascinating examples of magnetic architecture, where invisible field lines create channels and corridors that can hold vast quantities of solar material in seemingly impossible configurations. The filament that erupted on July 15th had been growing more unstable. With each passing day, astronomers could see the signs building magnetic stress accumulating like tension in a cosmic spring, waiting to release its stored energy. The sun's magnetic field is incredibly dynamic, constantly shifting and evolving as the star rotates and convects, creating conditions where structures like filaments can become increasingly unstable until they reach a critical threshold. When that threshold was finally crossed, the results were spectacular. The filament didn't simply disappear or fade away. Instead, it exploded outward in a violent cascade of plasma and magnetic fields, creating what's known as a coronal mass ejection, or CME. This represents one of the most powerful types of solar eruptions, capable of hurling billions of tons of stellar material into space at speeds that can exceed 3,000 kilometers per second. The explosion itself was captured in unprecedented detail by NASA's Solar Dynamics Observatory, a technological marvel that has been watching our sun continuously since 2010. This spacecraft represents the pinnacle of solar observation technology, equipped with instruments capable of imaging the sun in multiple wavelengths of light every few seconds, providing scientists with an unparalleled view of solar dynamics. The observatory's ability to capture the July 15th eruption from beginning to end showcases just how far our understanding of stellar phenomena has advanced. Through the observatory's instruments, we could watch as the filament became increasingly unstable, see the first signs of eruption as magnetic field lines began to snap and reconnect, and witness the spectacular cascade of plasma. As the structure collapsed and exploded outward, the images reveal a sun that is far from the static ball of light we might imagine from Earth, but rather a dynamic, seething cauldron of magnetic forces and superheated matter in constant motion. The visual spectacle of this eruption is difficult to describe in ordinary terms. Imagine watching a mountain range made of fire suddenly collapse and explode outward, creating avalanches of light that flow like luminous waterfalls through space. The plasma doesn't move in straight lines, but follows the invisible highways of magnetic field lines, creating graceful arcs and spirals that trace the complex geometry of stellar magnetism. What emerged from this cosmic violence was the canyon of fire itself, a temporary scar on the sun's surface that glowed with the heat of stellar fusion. The channel where the filament had previously been suspended now appeared as a bright canyon with walls of plasma reaching temperatures that dwarf anything found on Earth. This wasn't a permanent feature. The sun's magnetic field would eventually heal this wound, bringing new plasma into the region and restoring a semblance of order. But for a brief time, this canyon stood as testament to the incredible forces at work within our nearest star. The timing of this eruption is particularly significant because it occurred during what many scientists believe is the peak, or very near the peak, of solar cycle. 25, the Sun follows an 11-year cycle of magnetic activity, during which its magnetic poles actually flip, creating periods of increased solar activity known as solar. Maximum, we are currently in or approaching this maximum phase, which means events like the July 15th eruption are becoming more frequent and more intense. Understanding solar cycles helps us appreciate why eruptions like this canyon of fire are occurring with increasing frequency. The sun isn't simply a constant source of light and heat, but rather a dynamic magnetic dynamo that goes through regular cycles of activity during solar minimum. The sun is relatively calm with fewer eruptions and less dramatic activity, but as it approaches solar maximum, the magnetic field becomes increasingly tangled and stressed, leading to more frequent and more powerful eruptions. The science behind these magnetic cycles involves processes that are still not fully understood, despite decades of intensive study. The sun's magnetic field is generated deep within its interior through a complex interplay of rotation, differential heating and convection currents. This creates a magnetic dynamo that regularly reverses polarity, causing the Sun's north and south magnetic poles to switch places roughly every 11 years. As we approach the peak of this current solar cycle, we're witnessing firsthand the spectacular consequences of this magnetic choreography. The July 15th eruption serves as a perfect example of what happens when these magnetic forces reach their breaking point, creating events that reshape our understanding of stellar dynamics and remind us of the incredible power contained within our seemingly familiar Sun. But what exactly causes a filament to become so unstable that it creates such a dramatic eruption? The answer lies in the intricate dance of magnetic fields that permeate every layer of the solar atmosphere. These aren't simple dipolar fields like you might find around a bar magnet, but incredibly complex three-dimensional structures that twist and writhe through the solar corona like invisible serpents made of pure magnetic force. The filament that erupted on July 15th was essentially a massive rope of plasma held in place by magnetic field lines that had become increasingly twisted and stressed over time. Imagine trying to hold a heavy rope suspended in the air using only magnetic forces. The rope wants to fall due to gravity, but the magnetic fields create invisible supports that keep it aloft. However, as these magnetic structures become more and more twisted, they store increasing amounts of energy, like a spring being wound tighter and tighter. Eventually, the system reaches a point where it can no longer maintain this delicate balance. The magnetic field lines begin to snap and reconnect in a process that releases enormous amounts of stored energy almost instantaneously. This magnetic reconnection is one of the most fundamental processes in plasma physics, and it's responsible not only for solar eruptions, but for phenomena ranging from the northern lights on Earth to the dramatic particle jets observed around black holes throughout the universe. When magnetic reconnection occurs in a solar filament, the results are both beautiful and violent. The plasma that was previously held in a stable configuration suddenly finds itself free from its magnetic constraints and begins to flow along new field line geometries. Some of this material falls back toward the solar surface, creating spectacular cascades of luminous plasma, while other portions are accelerated outward into space at tremendous velocities. The July 15th event demonstrates this process on a truly massive scale as the filament became unstable and began to erupt. Billions of tons of plasma were simultaneously falling back toward the Sun and being ejected into interplanetary space. The falling material created the glowing canyon walls that made this event so visually striking, while the ejected material formed the coronal mass ejection that raced away from the Sun at speeds exceeding 1,000,000 miles per hour. To fully appreciate the violence of this eruption, consider that the energy released in just a few minutes was equivalent to billions of hydrogen bombs detonating simultaneously. Yet this represents just a tiny fraction of the total energy output of our Sun, which converts approximately 4 million tons of matter into pure energy every single second through nuclear fusion. The July 15th eruption, while spectacular by earthly standards, was merely a hiccup in the Sun's constant energy production. The coronal mass ejection created by this eruption carried with it not just plasma, but also magnetic fields frozen into the expanding cloud of stellar material. As this magnetized plasma travels through space, it can interact with planetary magnetic fields and atmospheres, creating a variety of effects. When such ejections are directed toward Earth, they can cause geomagnetic storms that disrupt satellite communications, interfere with power grids, and create spectacular auroral displays at high latitudes. Fortunately for Earth, the July 15th eruption was directed away from our planet. The orientation and location of the erupting filament meant that the resulting coronal mass ejection was aimed harmlessly into deep space, sparing us from any potential technological disruptions. This directional aspect of solar eruptions is largely a matter of chance, depending on where on the Sun's surface the instability occurs, and which way the magnetic fields happen to be pointing when the eruption takes place. However, this fortunate miss serves as a powerful reminder of what could happen when such eruptions are aimed in our direction. Our modern technological civilization is more vulnerable to space weather events than ever before. Satellites that provide GPS navigation, internet communications, and weather monitoring all operate in the harsh environment of space where they're directly exposed to solar radiation, and charged particles, power grids that span entire continents can be induced with dangerous electrical currents when Earth's magnetic field is disturbed by incoming solar material. The vulnerability of our technological infrastructure to space weather became dramatically apparent during the Great Geomagnetic Storm of 1859, known as the Carrington Event. This solar storm was so powerful that telegraph lines sparked and caught fire. Telegraph operators received electric shocks, and auroras were visible as far south as the Caribbean. If a similar event occurred today, the consequences could be catastrophic, affecting everything from banking systems to transportation networks to emergency services. Studying eruptions like the July 15th Canyon of Fire helps scientists better understand the mechanisms behind these potentially disruptive events by analyzing the magnetic configurations that lead to filament instabilities. Researchers hope to develop better predictive models that could provide earlier warnings of potentially Earth-directed solar eruptions. This research represents a crucial intersection of pure science and practical necessity, as our technological dependence continues to grow. The Solar Dynamics Observatory that captured this spectacular eruption represents one of humanity's most sophisticated attempts to monitor and understand our Sun. Launched in 2010, this remarkable spacecraft continuously observes the Sun in multiple wavelengths of light, providing unprecedented detail about solar phenomena. The observatory's atmospheric imaging assembly takes images spanning at least 1.3 solar diameters in multiple wavelengths, nearly simultaneously capturing everything from the relatively cool chromosphere to the million-degree corona. These multi-wavelength observations are crucial for understanding the complex processes involved in solar eruptions. Different temperatures of plasma emit light at different wavelengths. So by observing the Sun simultaneously in multiple colors, scientists can see how different layers of the solar atmosphere respond during events like the July 15th eruption. This creates a three-dimensional picture of the eruption process, showing how energy and material flow through the various layers of the solar atmosphere. The rapid imaging capability of the Solar Dynamics Observatory ensures that no significant solar event goes unobserved. The spacecraft takes images every 12 seconds in most wavelengths and every few minutes in others, providing the temporal resolution needed to understand the rapid evolution of solar phenomena during the July 15th eruption. This meant that scientists could watch in real time as the filament became unstable, began to erupt, and ultimately created the spectacular Canyon of Fire. What makes the July 15th eruption particularly valuable for scientific study is that it was observed from beginning to end, with multiple instruments operating simultaneously. This comprehensive dataset allows researchers to trace the entire sequence of events from the initial magnetic instabilities that triggered the eruption through the complex cascade of plasma flows that created the canyon to the formation and evolution of the resulting coronal mass ejection. The scientific community has been particularly excited about this event because it provides an unprecedented opportunity to test and refine our understanding of magnetic reconnection processes in real time. For decades, scientists have studied these phenomena through computer simulations and theoretical models, but having such a comprehensive observational dataset of an actual large-scale eruption allows researchers to validate their theories against reality and discover new aspects of plasma physics that weren't previously understood. One of the most intriguing aspects of the July 15th eruption is how it demonstrates the Sun's remarkable ability to heal itself after such a violent event within hours of the initial explosion. The solar magnetic field began the process of reorganizing itself, bringing new plasma into the canyon region and gradually restoring a more stable configuration. The self-healing property of stellar magnetic fields represents one of the most fascinating aspects of solar physics and helps explain how the Sun maintains its overall structure despite constant internal turbulence. The process of magnetic field reorganization following an eruption like this involves incredibly complex three-dimensional interactions between plasma and magnetic forces. As the initial violence of the eruption subsides, the Sun's magnetic field lines begin to settle into new configurations that can once again support the weight of suspended plasma against gravity. This creates the conditions for new filaments to form in the same general region. Though they may have slightly different orientations and characteristics than their predecessor, watching this healing process unfold through the eyes of the Solar Dynamics Observatory provides scientists with invaluable insights into how magnetic systems respond to sudden disruptions and how they evolve toward new equilibrium states. These observations have implications far beyond solar physics, as similar magnetic reconnection processes occur throughout the universe, from the magnetospheres of planets to the accretion disks around black holes. The timing of this eruption during the current solar maximum period makes it particularly significant for space weather forecasting as Solar Cycle 25 continues to evolve toward its peak. We can expect more events of similar or even greater magnitude. The challenge for scientists and space weather forecasters is to develop better methods for predicting when and where such eruptions might occur, and whether they'll be directed toward Earth. Current space weather prediction relies heavily on statistical models based on historical data and real-time monitoring of solar activity. While these methods have improved significantly over the past few decades, they still cannot provide the kind of precise forecasting that would be ideal for protecting our technological infrastructure. The July 15th eruption offers a valuable case study for improving these predictive capabilities by analysing the precursor conditions that led to this particular event. One of the most promising areas of research involves using artificial intelligence and machine learning techniques to analyse the vast amounts of data collected by solar observatories like the Solar Dynamics Observatory. These systems can potentially identify subtle patterns in magnetic field configurations and plasma flows that might indicate an impending eruption days or even weeks before it occurs. Such early warning capabilities could provide crucial time for satellite operators and power grid managers to take protective measures. The Canyon of Fire, created on July 15th, also provides unique opportunities to study the fundamental properties of solar plasma under extreme conditions. The temperatures and densities involved in this eruption represent some of the most extreme environments accessible to direct observation anywhere in the solar system by analysing the light emitted by this superheated plasma. Scientists can determine its composition, temperature, and velocity with remarkable precision. These measurements help validate our understanding of nuclear processes occurring within the Sun and provide insights into the behavior of matter under conditions that cannot be replicated in any earthly laboratory. The plasma physics revealed by events like this has applications ranging from fusion energy research to understanding the formation and evolution of stars throughout the universe. The visual spectacle of the July 15th eruption, captured by multiple wavelengths of light, reveals the intricate beauty hidden within what might initially appear to be cosmic violence. When viewed in extreme ultraviolet light, the erupting plasma creates graceful, flowing patterns that follow the invisible architecture of magnetic field lines. These images remind us that even the most violent stellar phenomena follow underlying physical laws that create their own form of cosmic choreography. The different wavelengths reveal different aspects of the eruption process. Cooler plasma appears in certain colors, while the hottest regions shine in others. By combining these multi-wavelength observations, scientists can create a comprehensive picture of how energy and material flow through the various layers of the solar atmosphere. During such events, this three-dimensional understanding is crucial for developing accurate models of solar eruption processes. Perhaps one of the most remarkable aspects of studying the July 15th eruption is how it connects us to the broader universe. The same magnetic reconnection processes that created this spectacular canyon of fire occur in stellar systems throughout our galaxy and beyond. By understanding these phenomena in our own solar system, we gain insights into the behavior of distant stars and the cosmic processes that shape the evolution of planetary systems. The scale of energy involved in this eruption also provides a humbling perspective on our place in the cosmos. The energy released in just a few minutes of this event exceeds the total energy consumption of human civilization over many years. Yet this represents merely a tiny fraction of the Sun's continuous energy output. This comparison helps us appreciate both the incredible power of stellar processes and the remarkable stability that allows life to flourish on Earth. Despite our proximity to such a dynamic and powerful star, as we continue to study events like the July 15th Canyon of Fire, we're reminded that our sun, while appearing constant and predictable from day to day, is actually an incredibly dynamic and complex magnetic system capable of sudden dramatic changes. The peaceful yellow orb that rises each morning harbours within its depths processes of such violence and beauty that they challenge our imagination and expand our understanding of the physical universe. The ongoing research into this eruption and others like it represents one of the most exciting frontiers in modern astronomy. Each new observation adds pieces to the puzzle of stellar behaviour and helps us better understand not only our own sun, but the countless other stars scattered throughout the cosmos. The July 15th event serves as a perfect example of how a single dramatic moment in space can illuminate fundamental processes that operate throughout the universe. Looking forward, the lessons learned from analysing this spectacular eruption will undoubtedly influence how we prepare for future space weather events. As Solar Cycle 25 continues to unfold, we can expect more such displays of stellar power, and each one provides new opportunities to test our understanding and improve our predictive capabilities. That's the Canyon of Fire carved into our sun on that remarkable July day represents far more than just a beautiful cosmic spectacle. It stands as a testament to the incredible forces that shape our solar system and a reminder of the ongoing dance between matter, energy, and magnetic fields that creates the dynamic universe we call home. The scientific instruments aboard the Solar Dynamics Observatory work tirelessly to decode the language of stellar phenomena, translating the sun's magnetic whispers into data that human minds can comprehend. Each wavelength of light carries its own story, revealing different temperatures, pressures, and velocities within the roiling solar atmosphere. When the July 15th filament erupted, these instruments captured not just the visual spectacle, but the underlying physics that govern such magnificent displays of cosmic power. Understanding how these observations translate into knowledge requires appreciating the sophisticated technology behind our solar surveillance. The observatory's Extreme Ultraviolet Variability Experiment monitors the sun's energy output across multiple wavelengths, while the helioseismic and magnetic imager maps the magnetic fields that orchestrate these dramatic events together. These instruments create a comprehensive portrait of solar activity that would have been unimaginable just decades ago. The data collected during the July 15th eruption reveals fascinating details about how magnetic energy builds and releases within stellar atmospheres. Scientists can trace the flow of plasma as it follows invisible magnetic highways, see how temperatures change during the reconnection process, and measure the speeds at which material is ejected into space. This wealth of information helps researchers understand not just what happened, but why it happened, and potentially when similar events might occur again. One of the most intriguing aspects of this particular eruption is how it demonstrates the interconnected nature of solar phenomena. The collapse of a single filament doesn't occur in isolation, but triggers a cascade of effects throughout the surrounding coronal magnetic field lines that were previously stable, suddenly find themselves in new configurations. Plasma that was quietly flowing along established paths is redirected into chaotic turbulent streams, and the entire local magnetic environment undergoes a rapid and dramatic transformation. This interconnectedness means that predicting solar eruptions requires understanding not just individual magnetic structures, but the complex web of relationships between them. A filament that appears stable in isolation might become unstable when neighbouring magnetic fields shift, or when changes in the sun's rotation alter the stress patterns throughout the corona. The July 15th event provides a perfect case study of how these subtle interactions can lead to spectacular consequences. The plasma physics revealed by this eruption also offers insights into fundamental processes that occur throughout the universe. Magnetic reconnection, the driving force behind the Canyon of Fire, operates in environments ranging from Earth's magnetosphere to the cores of distant galaxies. By studying these processes in our own solar system, where we can observe them in exquisite detail, scientists develop understanding that applies to cosmic phenomena far beyond our immediate neighborhood. The temperatures involved in the July 15th eruption represent some of the most extreme conditions in our solar system. The plasma within the canyon walls reached temperatures exceeding 10 million degrees Celsius, hot enough to strip electrons from even the heaviest atoms and create a state of matter where the normal rules of chemistry simply don't apply. At these temperatures, matter exists as a fully ionized gas, where atomic nuclei and electrons move independently, creating the luminous flowing streams that make solar eruptions so visually striking. These extreme conditions also provide natural laboratories for testing our understanding of physics under circumstances that cannot be replicated on Earth. The behavior of matter at such temperatures and densities offers insights into nuclear processes, stellar evolution, and the fundamental interactions between particles and fields that shape the structure of the universe. The July 15th eruption essentially gave scientists a front-row seat to observe cosmic physics in action. The magnetic architecture that created and ultimately destroyed the erupting filament represents one of the most complex and beautiful aspects of solar physics. These aren't simple magnetic field lines, but intricate three-dimensional structures that twist and weave through the solar atmosphere like cosmic DNA. The filament itself was held in place by magnetic forces that could suspend billions of tons of plasma against the tremendous gravitational pull of the Sun, demonstrating the incredible strength and precision of stellar magnetic fields. When this magnetic architecture finally became unstable, the resulting reorganization created the canyon of fire that captured the world's attention. The process involves magnetic field lines snapping and reconnecting in patterns that release enormous amounts of stored energy, while simultaneously creating new configurations that will eventually support new plasma structures. This cycle of building tension and explosive release represents one of the fundamental rhythms of stellar activity. The speed at which these magnetic reconfigurations occur is truly remarkable. During the July 15th eruption, magnetic field lines that had been stable for weeks or months suddenly snapped and reconnected in a matter of minutes, releasing energy equivalent to billions of nuclear weapons. The resulting plasma flows reached velocities of hundreds of kilometers per second, creating the spectacular cascades and fountains of luminous material that define this event. Understanding these rapid magnetic changes requires sophisticated computer models that can simulate the complex interactions between plasma and magnetic fields. Researchers use supercomputers to recreate the conditions leading up to eruptions like the July 15th event, testing different scenarios and comparing their results with actual observations. This computational approach helps scientists identify the key factors that determine when and how magnetic instabilities develop. The role of the Sun's rotation in creating and maintaining magnetic structures like filaments adds another layer of complexity to understanding solar eruptions. As the Sun rotates, different parts of its surface move at different speeds, with the equator completing a rotation in about 25 days, while the polar regions take closer to 35 days. This differential rotation continuously twists and stretches magnetic field lines, creating the complex topologies that can support filaments and other magnetic structures. The July 15th filament had likely been shaped by months or even years of this differential rotation, gradually building up the magnetic stress that would eventually lead to its spectacular collapse. The precise timing of the eruption depended on subtle changes in the local magnetic environment, possibly triggered by the emergence of new magnetic flux from deep within the Sun or by interactions with neighboring magnetic structures. The coronal mass ejection created by this eruption represents another fascinating aspect of stellar physics, as the erupting plasma and magnetic fields race away from the Sun. They carry with them a piece of the solar magnetic field, creating a magnetized cloud that can interact with planetary environments throughout the solar system. These traveling magnetic structures can compress and distort planetary magnetospheres, create spectacular auroral displays, and in extreme cases, disrupt technological systems. The fact that the July 15th coronal mass ejection was directed away from Earth highlights the somewhat random nature of space weather. While scientists can often predict that an eruption will occur, they cannot always determine in advance which direction the resulting material will travel. This directional uncertainty represents one of the greatest challenges in space weather forecasting and emphasizes the importance of continuous solar monitoring. The healing process that followed the July 15th eruption reveals another remarkable aspect aspect of solar dynamics within hours of the initial explosion. The sun's magnetic field began reorganizing itself, bringing new plasma into the canyon region and starting the process of rebuilding the magnetic structures that had been destroyed. This self-healing capability demonstrates the incredible resilience of stellar magnetic systems and their ability to maintain overall stability despite frequent violent disruptions. Watching this recovery process through the continuous observations of the Solar Dynamics Observatory provides scientists with unique insights into how complex magnetic systems respond to sudden perturbations, the gradual filling of the canyon with new plasma, the reformation of magnetic field lines, and the eventual establishment of new equilibrium conditions all occur according to physical laws that govern magnetic and plasma interactions throughout the universe. The educational value of events like the July 15th eruption extends far beyond the scientific community. These spectacular displays of cosmic power capture public imagination and inspire new generations of scientists and engineers. The visual beauty of the Canyon of Fire combined with the underlying physics makes solar astronomy accessible to people who might otherwise never consider the complexity and wonder of stellar phenomena. The images and videos captured during this eruption have been viewed by millions of people around the world, bringing the reality of space weather and solar dynamics into homes and classrooms everywhere. This public engagement is crucial for building support for continued space weather research and for educating people about the potential impacts of solar activity on our technological civilization. As Solar Cycle 25 continues to evolve toward its maximum phase, we can expect more events similar to or even more spectacular than the July 15th eruption. Each new event provides additional opportunities to test our understanding, refine our models, and improve our predictive capabilities. The cumulative knowledge gained from studying multiple eruptions helps scientists identify common patterns and underlying principles that govern solar activity. The international cooperation required to study events like the July 15th eruption demonstrates how modern astronomy has become a truly global enterprise. Data from the Solar Dynamics Observatory is shared with researchers around the world who contribute their expertise in plasma physics, magnetic field theory, and computational modeling. This collaborative approach ensures that each solar event is analysed from multiple perspectives, maximising the scientific return from these spectacularly natural experiments. The technological spin-offs from solar research also benefit society in unexpected ways. The advanced imaging techniques developed for solar observation find applications in medical imaging and materials science. The computational methods used to model solar magnetic fields contribute to research in fusion energy and plasma processing, and the space weather prediction systems protect not only satellites and power grids, but also the safety of astronauts and airline passengers. Looking ahead, the lessons learned from the July 15th Canyon of Fire will undoubtedly influence how we prepare for future challenges as human activity expands beyond Earth. Our vulnerability to space weather will only increase lunar bases. Mars missions and deep space exploration will all require sophisticated space weather forecasting capabilities based on the kind of fundamental understanding that events like this eruption help provide. The July 15th event also reminds us that despite all our technological advances and scientific knowledge, we remain intimately connected to the cosmic forces that shaped our solar system. The same nuclear fusion processes that created the energy for this spectacular eruption also provide the steady stream of light and warmth that makes life on Earth possible. We are quite literally children of the stars, living in the gentle embrace of stellar energy. The magnetic field that orchestrated this cosmic drama also plays a crucial role in protecting Earth from harmful cosmic radiation and maintaining the delicate balance of our planet's atmosphere. Understanding how these magnetic systems work and occasionally fail helps us appreciate the remarkable conditions that allow our blue world to thrive in the vast emptiness of space. As we continue to study and marvel at events like the July 15th Canyon of Fire, we're reminded that astronomy is not just about distant objects and abstract concepts, but about understanding our place in a dynamic and interconnected universe. Every solar eruption tells a story about the fundamental forces that govern cosmic evolution, and every observation brings us closer to comprehending the magnificent complexity of the stellar realm we call home. The ongoing study of the July 15th eruption reveals layers of complexity that continue to surprise researchers as they delve deeper into the vast datasets collected during those dramatic hours when magnetic forces reshaped a portion of our star's surface. The sheer volume of information captured by multiple instruments operating simultaneously creates a treasure trove of scientific data that will likely be analysed for years to come. Each wavelength of light, each temperature measurement, each velocity calculation adds another piece to the puzzle of understanding how stellar magnetic systems behave under extreme stress. What makes this particular event so scientifically valuable is the unprecedented level of detail with which it was observed. Previous solar eruptions were often caught in partial glimpses or studied after the fact using indirect evidence. But the July 15th Canyon of Fire was monitored from its earliest precursor signs, through its explosive climax to its gradual aftermath. This comprehensive coverage allows scientists to construct a complete timeline of events and understand the subtle processes that trigger such magnificent displays of cosmic power. The precursor activity leading up to the eruption tells its own fascinating story for several days before the main event. Astronomers noticed subtle changes in the magnetic field configuration around the filament. These weren't dramatic shifts, but rather gentle adjustments in field line geometry that suggested building tension within the magnetic structure. It's similar to watching a rope slowly stretch under increasing weight. You can see the fibers beginning to strain long before the final dramatic snap that breaks the rope entirely. These early warning signs represent one of the most promising areas for improving space weather prediction. If scientists can learn to recognize the magnetic signatures that precede major eruptions, they might be able to provide days or even weeks of advance warning for potentially Earth-directed events. The July 15th eruption provides an excellent case study for developing these predictive capabilities because it was so thoroughly documented from beginning to end. The role of small-scale magnetic reconnection events in triggering larger eruptions became particularly apparent. During the July 15th event, researchers observed numerous minor reconnection episodes in the hours leading up to the main eruption, each releasing small amounts of energy and slightly altering the local magnetic environment. These micro-events appear to have destabilized the overall magnetic structure, gradually weakening the forces that held the massive filament in place. This cascade effect, where small disturbances grow into major eruptions, represents one of the most intriguing aspects of solar physics. It suggests that the sun's magnetic field exists in a delicate balance, where even minor perturbations can have far-reaching consequences. Understanding these trigger mechanisms could revolutionize our ability to predict when and where major eruptions might occur. The three-dimensional structure of the erupting filament, revealed through multi-wavelength observations, shows a level of complexity that challenges our current theoretical models, rather than a simple rope-like structure. The filament exhibited twisted helical patterns that wound through multiple layers of the solar atmosphere like a cosmic double helix. These intricate geometries reflect the complex history of magnetic field evolution that created and sustained the structure over its lifetime. When this twisted magnetic architecture finally became unstable, the resulting eruption followed patterns that traced the invisible pathways carved by magnetic forces. Plasma didn't simply explode outward randomly, but flowed along specific routes determined by the underlying field geometry, creating the spectacular arcs and cascades that made this event so visually striking. The July 15th eruption essentially provided a visible map of invisible magnetic highways that normally remain hidden from view. The energy budget of this eruption continues to astound researchers. Calculations suggest that the total energy released during the event exceeded 10 to the 32nd power joules, roughly equivalent to the energy that would be released by detonating 1 trillion hydrogen bombs simultaneously. Yet this enormous energy output represents less than 1/1000th of the Sun's total energy production over the same time period. This comparison illustrates both the incredible violence of solar eruptions and the almost incomprehensible power of stellar fusion processes, the efficiency with which magnetic reconnection converts stored magnetic energy into kinetic energy during events like the July 15th eruption, provides insights into fundamental plasma physics processes that operate throughout the universe. Similar reconnection events occur in Earth's magnetosphere during geomagnetic storms in the accretion disks around black holes, and in the formation of galactic jets that extend across millions of light years studying these processes in our own solar system, where they can be observed in exquisite detail, help scientists understand cosmic phenomena that would otherwise remain mysterious. The aftermath of the July 15th eruption proved almost as fascinating as the event itself, as the initial violence subsided and the sun began its healing process. Researchers observed the gradual reformation of magnetic structures in the canyon region. New field lines emerged from below the surface, bringing fresh plasma into the evacuated region and slowly rebuilding the magnetic architecture that had been destroyed. The entire recovery process unfolded over several days, providing a time-lapse view of how stellar magnetic systems reorganize themselves after major disruptions. This self-healing capability represents one of the most remarkable aspects of solar dynamics. Despite experiencing violent eruptions that tear apart magnetic structures and scatter plasma across vast distances, the Sun consistently rebuilds these systems and returns to a state of relative stability. The mechanisms behind this recovery involve complex interactions between magnetic diffusion plasma flows and convective motions deep within the solar interior. The temperature variations observed during the canyon formation reveal the incredible range of conditions that exist simultaneously within the solar atmosphere, while the hottest regions of the erupting plasma reach temperatures exceeding 10 million degrees Celsius. Cooler areas within the same structure maintain temperatures closer to 1 million degrees. This temperature diversity reflects the complex thermodynamics of magnetic reconnection, where different regions experience varying degrees of heating depending on their proximity to reconnection sites. The cooling mechanisms that gradually reduce the canyon's temperature over time provide insights into how energy dissipates in stellar atmospheres. The hot plasma loses energy through radiation, conduction, and expansion, creating a gradual transition from the initial explosive heating to the more moderate temperatures that characterize the healed region. Understanding these cooling processes helps scientists model how energy flows through stellar atmospheres and how magnetic eruptions affect the overall energy balance of stars. The magnetic field measurements taken during the July 15th eruption reveal field strengths that far exceed anything achievable in terrestrial laboratories. Some regions within the erupting structure exhibited magnetic fields thousands of times stronger than Earth's magnetic field, creating conditions where magnetic pressure dominates over gas pressure and fundamentally alters the behavior of plasma. These extreme magnetic environments provide natural laboratories for testing theoretical predictions about plasma behavior under conditions that cannot be replicated artificially. The propagation of the coronal mass ejection away from the Sun follows patterns that reflect the complex interplay between the ejected material and the ambient solar wind. The magnetized plasma cloud created by the eruption interacts with the existing flow of particles streaming away from the Sun, creating shock waves, compression regions, and turbulent mixing zones that extend the influence of the eruption far beyond the immediate vicinity of the Sun. Tracking the evolution of this coronal mass ejection as it travels through interplanetary space provides valuable data for understanding how solar disturbances propagate throughout the solar system. The magnetic field embedded within the ejected material carries with it information about the conditions at the eruption site, allowing scientists to study solar magnetic processes using measurements taken by spacecraft positioned throughout the solar system. The radio emissions generated during the July 15th eruption created a distinctive signature that radio astronomers detected across multiple frequencies. These electromagnetic signals provide complementary information about the eruption process, particularly regarding the acceleration of charged particles and the generation of plasma waves, the radio data helps scientists understand how magnetic reconnection creates the high-energy particle populations that can pose radiation hazards to spacecraft and astronauts. The correlation between radio emissions and visual observations of the eruption demonstrates the value of multi-wavelength astronomy, where different types of electromagnetic radiation reveal different aspects of the same physical processes. The radio signals can penetrate regions of dense plasma that might obscure optical observations, providing insights into the interior structure of erupting magnetic systems. The impact of the July 15th eruption on the broader solar corona extended far beyond the immediate vicinity of the canyon itself. The violent redistribution of magnetic energy created waves and disturbances that propagated throughout the corona, affecting plasma flows and magnetic field configurations across vast areas of the solar atmosphere. These global effects demonstrate how localized magnetic instabilities can influence the entire coronal environment. The study of these far-field effects helps scientists understand how individual eruptions contribute to the overall dynamics of the solar corona, and how the cumulative effect of many small eruptions shapes the large-scale structure of the solar magnetic field. This global perspective is crucial for developing comprehensive models of solar activity that can account for the complex interactions between different magnetic systems. The isotopic composition of the plasma ejected during the July 15th eruption provides a unique window into the nuclear processes occurring deep within the solar core. The material expelled during major eruptions carries with it isotopic signatures that reflect the fusion reactions responsible for the sun's energy production. By analyzing these signatures, scientists can test theoretical models of stellar nucleosynthesis and gain insights into the internal structure and evolution of stars. The abundance ratios of different elements in the ejected material also provide information about the convective processes that transport material from the solar interior to the surface. These measurements help constrain models of stellar structure and evolution, contributing to our understanding of how stars like our Sun change over billions of years. The particle acceleration mechanisms operating during the July 15th eruption created populations of high-energy protons and electrons that reached velocities approaching significant fractions of the speed of light. These energetic particles provide insights into the fundamental physics of magnetic reconnection and shock acceleration processes that operate in astrophysical environments throughout the universe. The energy spectra and angular distributions of these accelerated particles reveal details about the magnetic field geometries and electric field structures present during the eruption. This information helps scientists understand how magnetic reconnection can efficiently convert stored magnetic energy into kinetic energy of individual particles, a process that has implications for understanding cosmic ray acceleration in supernova remnants, stellar winds, and other high-energy astrophysical phenomena. The July 15th eruption also provided an opportunity to test and refine computer models of solar magnetic activity. Researchers used sophisticated magneto-hydrodynamic simulations to recreate the conditions leading up to the eruption and compare their results with actual observations. This validation process helps identify strengths and weaknesses in current theoretical understanding and guides the development of more accurate predictive models. The computational challenges involved in modeling events like the July 15th eruption push the boundaries of current supercomputing capabilities, accurately simulating the complex three-dimensional interactions between magnetic fields and plasma requires enormous computational resources and sophisticated numerical algorithms. The ongoing development of these modeling capabilities represents a crucial investment in our ability to understand and predict solar activity. The educational impact of the July 15th eruption extends far beyond the scientific community. The spectacular images and videos captured during the event have been incorporated into astronomy curricula around the world, helping students visualize the dynamic processes that govern stellar behavior. The event serves as a perfect example of how scientific research can capture public imagination while advancing our understanding of fundamental physical processes. The international collaboration required to fully analyze the July 15th eruption demonstrates the global nature of modern solar physics. Research data sharing agreements between space agencies ensure that observations from multiple spacecraft and ground-based observatories are combined to create the most comprehensive possible picture of solar events. This collaborative approach maximizes the scientific return from expensive space missions and ground-based facilities. The technological innovations developed for solar observation continue to find applications in other fields. The advanced image processing techniques used to analyze solar eruption data contribute to medical imaging research. The high-speed data acquisition systems developed for solar observatories influence the design of industrial monitoring equipment, and the radiation-hardened electronics required for solar missions benefit satellite technology across multiple applications. The long-term monitoring capabilities demonstrated by missions like the Solar Dynamics Observatory provide a foundation for understanding solar variability over multiple solar cycles. By observing events like the July 15th eruption within the context of the 11-year solar cycle, scientists can identify patterns and trends that might not be apparent from isolated observations. This long-term perspective is crucial for understanding how solar activity affects Earth's climate and space environment. The July 15th Canyon of Fire stands as a testament to the incredible power and beauty of stellar magnetic processes, serving as both a spectacular natural phenomenon and a valuable scientific laboratory. The event reminds us that our Sun, while appearing constant and predictable, is actually a dynamic and sometimes violent magnetic system, capable of sudden dramatic changes that can reshape its surface and influence conditions throughout the solar system. As we continue to study and learn from events like the July 15th eruption, we gain not only scientific knowledge but also a deeper appreciation for the cosmic forces that shape our existence. The same nuclear fusion processes that created the energy for this spectacular display also provide the steady flow of light and warmth that makes life on Earth possible, connecting us intimately to the stellar processes that govern our solar system. The ongoing analysis of this remarkable event continues to yield new insights into solar physics, with each new discovery adding to our understanding of how magnetic fields, plasma, and energy interact in stellar environments. The July 15th Canyon of Fire represents far more than just a beautiful cosmic spectacle. It stands as a crucial piece in the vast puzzle of understanding how stars work and how their activity affects the worlds that orbit them. The implications of understanding events like the July 15th Canyon of Fire extend far beyond academic curiosity into the very practical realm of protecting our increasingly connected and technologically dependent civilization. As we've become more reliant on satellites for everything from navigation to communication to financial transactions, our vulnerability to space weather events has grown exponentially. A coronal mass ejection directed toward Earth could potentially cause widespread disruptions that would affect billions of people around the globe. The economic consequences of a major space weather event targeting our planet could reach into the trillions of dollars as satellites fail, power grids collapse, and communication networks go dark. The ripple effects would cascade through every aspect of modern life, from transportation systems that rely on GPS navigation to financial markets that depend on satellite communications. The July 15th eruption serves as a sobering reminder of the potential for such disruptions, even though this particular event was harmlessly directed away from Earth. Preparing for future space weather threats requires not only continued scientific research, but also practical engineering solutions and policy frameworks that can protect critical infrastructure. Satellite operators are developing more radiation-resistant electronics and improved shielding systems, while power grid managers are implementing protective protocols that can isolate vulnerable components during geomagnetic storms. These efforts represent a growing recognition that space weather is not just a scientific curiosity, but a genuine threat to modern civilization. The international cooperation required for effective space weather monitoring and prediction continues to expand as nations recognize that solar eruptions respect no political boundaries. Data-sharing agreements between space agencies ensure that observations from spacecraft positioned throughout the solar system can be combined to provide the most comprehensive possible warning of potentially dangerous solar events. This global approach to space weather monitoring represents one of the most successful examples of international scientific cooperation. The educational value of spectacular events like the July 15th eruption cannot be overstated in inspiring the next generation of scientists and engineers. The visual drama of the Canyon of Fire captures imaginations in ways that textbooks and lectures alone cannot achieve. Students who witness such cosmic spectacles often develop lifelong interests in astronomy, physics, and space technology, contributing to the scientific workforce needed to address future challenges in space weather prediction and mitigation. The technological legacy of solar research continues to benefit society in unexpected ways. The advanced materials developed for space-based solar observatories find applications in everything from medical devices to renewable energy systems. The image processing algorithms created to analyze solar data contribute to advances in artificial intelligence and machine learning, while the precision timing systems required for space weather monitoring improve GPS accuracy and internet synchronization. As we look toward the future, the lessons learned from studying the July 15th eruption will undoubtedly influence how humanity prepares for its expansion beyond Earth. Lunar colonies and Mars settlements will be even more vulnerable to space weather than our current satellite infrastructure, requiring sophisticated prediction systems and protective technologies based on our growing understanding of solar dynamics. The July 15th Canyon of Fire also reminds us of the remarkable stability that has allowed life to flourish on Earth despite our proximity to such a dynamic and powerful star. The same magnetic field that can create spectacular eruptions also deflects most of the sun's harmful radiation, protecting our planet's atmosphere and making complex life possible. This delicate balance between stellar power and planetary protection represents one of the most fortunate circumstances in our solar system. The ongoing study of solar magnetic processes reveals fundamental principles that operate throughout the universe, from the smallest laboratory plasmas to the largest galactic structures. Magnetic reconnection drives phenomena across an incredible range of scales, connecting the July 15th eruption to the formation of stellar jets, the acceleration of cosmic rays, and the evolution of galactic magnetic fields. The philosophical implications of witnessing such cosmic events invite us to contemplate our place in the vast universe. When we observe a canyon of fire stretching across 250,000 miles of stellar surface, we're reminded that Earth is but a tiny speck in a cosmos filled with forces of unimaginable power. Yet this same perspective also highlights the preciousness of our world and the remarkable chain of circumstances that has allowed consciousness to emerge and contemplate the universe that created it. The July 15th eruption stands as a perfect example of how modern astronomy combines cutting-edge technology with fundamental physics to reveal the hidden workings of the cosmos. The same instruments that captured this spectacular event continue to monitor our sun, providing early warning of potentially dangerous solar activity, while advancing our understanding of stellar physics with each new observation. As Solar Cycle 25 continues its journey toward maximum, we can expect more such displays of stellar magnificence, each providing new opportunities to test our theories, refine our models, and improve our predictive capabilities. The cumulative knowledge gained from studying multiple eruptions helps scientists identify the subtle patterns and underlying principles that govern solar behavior. The international scientific community's response to the July 15th eruption demonstrates how quickly modern astronomy can mobilize to study transient phenomena within hours of the initial observation. Researchers around the world were analyzing data-sharing results and collaborating on interpretations. This rapid response capability ensures that maximum scientific value is extracted from each spectacular solar event. The July 15th Canyon of Fire will be remembered not just as a beautiful cosmic spectacle, but as a crucial milestone in our understanding of solar dynamics. The comprehensive dataset collected during this event will likely influence solar physics research for decades to come, providing a benchmark against which future eruptions can be compared and theoretical models can be tested. As we conclude our journey through this remarkable cosmic event, we're left with a profound appreciation for the dynamic nature of our nearest star and the incredible forces that shape our solar system. The July 15th eruption reminds us that astronomy is not just about distant objects and abstract concepts, but about understanding the very environment in which our planet exists and the cosmic processes that continue to influence our world. The canyon of fire that briefly scarred our sun's surface has healed, but the knowledge gained from studying this spectacular event will endure, contributing to our growing understanding of stellar magnetic processes and our ability to predict and prepare for future space weather events in a universe filled with dynamic and sometimes violent phenomena. The July 15th eruption stands as a testament to both the power of cosmic forces and the remarkable human capacity to observe, understand, and learn from the cosmos that surrounds us. So, as you drift off to sleep tonight, perhaps gazing up at the same sun that created this magnificent display, remember that you are witnessing a star in the prime of its magnetic activity, a cosmic performer capable of sudden dramatic acts that reshape its surface and influence conditions throughout our solar system. The gentle light that warms our days carries within it the memory of countless eruptions like the July 15th Canyon of Fire, reminding us that we live in a universe where beauty and violence dance together in an eternal cosmic ballet. The beauty of the July 15th Canyon of Fire lies not just in its spectacular visual display, but in what it reveals about the fundamental nature of stellar evolution and the delicate balance that governs our solar system. As we've journeyed through the science behind this remarkable event, we've discovered that our sun is far more complex and dynamic than the steady yellow orb we observe each morning might suggest. The magnetic architecture that created this cosmic spectacle operates according to principles that extend far beyond our solar system. The same reconnection processes that carved a 250,000-mile canyon across our star's surface also drive the formation of planetary auroras, power the jets of distant quasars, and shape the magnetic fields of galaxies throughout the universe. In studying the July 15th eruption, we're not just learning about our sun, but gaining insights into cosmic processes that operate on scales both unimaginably large and surprisingly intimate. The timing of this event during solar cycle 25 reminds us that we are living through a particularly active period in our star's 11-year magnetic cycle. The months and years ahead may bring even more spectacular displays of solar power, each offering new opportunities to witness the magnificent interplay between magnetic fields and stellar plasma. These future events will undoubtedly build upon the knowledge gained from analysing the July 15th eruption, creating an ever more complete picture of how our sun behaves and evolves. What makes events like the Canyon of Fire so profoundly moving is how they connect us to the broader story of cosmic evolution. The energy that created this spectacular display began its journey in the sun's core, where hydrogen nuclei fused to form helium in a process that has continued for over 4 billion years. This same nuclear fusion provides the steady stream of energy that makes life on Earth possible, linking every living thing on our planet to the stellar processes we've explored tonight. The instruments that captured this remarkable event represent humanity's most sophisticated attempt to understand our cosmic environment. The Solar Dynamics Observatory and its companion missions continue their tireless vigil, monitoring our sun's every magnetic whisper and preparing us for whatever stellar surprises may come. These technological marvels serve as our early warning system, our scientific laboratory, and our window into the fundamental forces that shape the universe. As we consider the implications of space weather for our technological civilization, the July 15th eruption serves as both warning and inspiration. While it reminds us of our vulnerability to cosmic forces beyond our control, it also demonstrates our remarkable ability to observe, understand, and prepare for such events. The same scientific curiosity that drives us to study spectacular solar eruptions also motivates us to develop the technologies and strategies needed to protect our increasingly connected world. The international cooperation required to fully analyze events like the Canyon of Fire reflects the best aspects of human nature. When faced with phenomena that transcend national boundaries and challenge our understanding of the universe, scientists from around the world come together to share data, insights, and expertise. This collaborative spirit ensures that each solar eruption advances our collective knowledge and brings us closer to mastering the art of space weather prediction. Perhaps most remarkably, the July 15th eruption reminds us that we are witnesses to an ongoing cosmic story that began billions of years ago and will continue long after our current civilization has faded into history. The sun that created this magnificent display has been burning steadily for longer than complex life has existed on Earth, and it will continue to shine for billions of years to come, creating countless more such spectacles for future observers to study and admire. The canyon of fire that briefly adorned our star's surface has long since healed, but the memory of this cosmic event lives on in the scientific data that continues to yield new insights into stellar behavior. Each measurement taken during those dramatic hours adds another piece to the vast puzzle of understanding how stars work, how magnetic fields evolve, and how the universe continues to surprise and delight us with its endless capacity for beauty and wonder. And so, dear stargazers, as you settle into the gentle embrace of evening and prepare for sleep, remember that the same sun that rises each morning with such reliable constancy is also capable of sudden, dramatic displays of cosmic artistry. The July 15th Canyon of Fire stands as a testament to the magnificent complexity hidden within familiar things and the endless capacity of the universe to surprise, inspire, and humble us with its grandeur. Sweet dreams, fellow travellers through space and time, and may your rest be filled with visions of stellar fires dancing across the cosmos, reminding us always of our precious place in this vast and wonderful universe we call home.